Good afternoon, dear faculty, researchers, KTH students, and friends from other outside KTH. It's a great pleasure to welcome you to the public lecture by Noel Gorelick from Google about planetary analysis with Google Earth engine. I'm Yifang Ban. I'm a professor of geoinformatics and director of Division of Geoinformatics within the School of Architecture and Built Environment at KTH. I'm also affiliated with the KTH Space Center. KTH Space Center organizes public lectures several times a year, topics ranging from plasma physics to aerospace engineering to Earth observation. When we planned the lecture for this year, also the time I met Noel at the ESA conference, I thought about the possibility of inviting him to talk about the latest development of Google Earth engine. And we also have 3 courses running this period with advanced remote sensing and 2 courses in GIS. I thought this would fit really well to have Noel here. So it's a really great pleasure to have you here, Noel. And a few words about Noel. He's a software engineer at Google and founder of Google Earth engine. He joined Google in 2007 and has been working with big data analysis and visualization, several projects on this. He's the author of Google Moon and Google Mars. And before he joined Google, he has helped to launch 7 interplanetary missions to 2 planets and a moon. So please, let's welcome Noel Gorelick. Thank you.
Thank you. That intro was my first slide. So I'm a software engineer at Google. I've been there 8 years. As was just said, prior to going to Google, I used to send spacecraft to Mars. I worked on every American spacecraft mission to Mars after Pathfinder that didn't crash, which was 6 of them. So that was a fun job, fun career. And while I was doing that, putting together maps of Mars, Google released Google Maps in 2005. And one of the engineers that worked with me at the time cold called Google and said, hey, can we have the source code for Google Maps so we can make Google Mars? And through blind dumb luck, he happened to get to the right person at Google who said no, but that sounds like a great project, come out and we'll build it. So we go out, we build Google Mars. In the first 2 weeks, we have a working prototype. It's not perfect because you can still put the interstate system on top of Mars, but it was kind of cool and it worked. And they said, would you like a job? The engineer that went with me said, yo, I'm in. I was still having fun sending stuff to Mars. But while I was there working on this project, they said, hey, we see you're working on your dissertation. Would some CPUs help? And I'm a computer scientist, so CPUs always help. And I said, that'd be great. They said, here's 20,000 CPUs, let us know when you're done. They gave me an entire data center. And it was so transformative to my science that I actually didn't finish my dissertation. I was able to work on projects at a scale that I'd never even thought of before. And so I ran off and did that. 14 months later, when I decided that the job at Google looked like more fun than sending stuff to Mars, think about that for a second, I finally said, okay, that's what I want to do. I want to use your resources to make science better. And they said, okay, come do that. So my job at Google is to take Google's resources, apply them to science, and make science suck less. And science is kind of hard, and it shouldn't be. There's a lot of parts of science that are just needlessly complex that once someone's done it once, it shouldn't have to be done again. So some of the projects I worked on while I was at Google were Google Mars and Google Moon, which seems obvious, seeing as how I sent spacecraft to other planets. But along came Google Earth Engine, which is a platform for doing really big-scale scientific analysis. I'm going to tell you about it, and I'm going to tell you about some of the background about how we got here. So Google's mission, you've probably seen this before, organize the world's information. My part of that, again, the scientific part of the information, but there's a lot of it. especially when you get to working with spacecraft. There's a lot of spacecraft data. Some of it's complex, hard to use, definitely hard to get to. And the world up to now has been, if you want to work on data from, say, the Landsat mission, you would get a $3 million grant. You would hire a bunch of grad students, get some system administrators, buy a bunch of hard drives, some computers, start downloading data, and somewhere between 9 months and a year later, you'd be ready to start doing some analysis, which is silly. If you want to do radar data, you would get another $3 million grant, go through the same process, and those are basically two disparate data sets that are rather tricky to put together. If you then want to bring in, say, atmospheric data, you go through the whole process again. And every single lab on the planet has to do this same thing. Why? Once it's done once, why should anybody have to do it again? So that's sort of how we got here. I'm going to lay out what Earth Engine is and how it works through a series of stories. And the first story I'm going to relate to you is about the Landsat mission. Who doesn't know what Landsat is? Okay, all right. So in the 70s, the USGS and NASA launched an Earth-observing satellite called Landsat 1. Didn't last very long, did a good job, did a good enough job that they've now launched Landsats 2 through 7 as well. Somewhere around 1984, Landsat 5 launched, and since then, we've had essentially a continuous, unbroken record of the planet's surface. The Landsat instrument is not just a normal camera. The camera in your phone takes RGB pictures. If you fiddle with it a little bit, you can get some near-infrared out of it because it has a big panchromatic sensor. The Landsat sensor takes, depending on which one it is, 7 or 10 bands of data. So in addition to red, green, and blue, it also has near-IR, shortwave infrared, and some thermal bands. And with all these extra bands, you can do a lot more than just look at see what's on the Earth. You can actually start distinguishing between different things. So you can distinguish between different kinds of trees, different kinds of crops, different kinds of minerals on the surface. So all these extra bands let you do some discrimination. All that extra data means that the data is not completely trivial to use. If I gave you a red, green, blue image that I took off my phone, you'd probably know what to do with it. You might be able to find some objects in it, maybe even put it through some kind of machine learning. All these additional bands and the fact that there are multiple resolutions, multiple projections, make the data a little non-trivial to use. It just so happens that in about 2008, the Landsat data became free. They used to charge per image, and it is no coincidence that our project also started in 2008. When the Landsat data became free, we saw an opportunity to take this data that was somewhat hard to use and very difficult to get and make it trivial to use and trivial to operate with. This is a picture of Hawaii seen through multiple bands of the Landsat sensor, discriminating different types of materials. So the Landsat data, back in when I made this slide a couple of years ago, was collected, well, it still is collected at a bunch of remote receiving stations. So Landsat 5 had a sensor malfunction, a transmitter malfunction, so you could only get data from it when it was directly overhead. It used to be that it would put it on tape and it would store it, and then it would download everything when it got near a receiving station. But the tape recorder broke, and you could only get data when it was flying over a receiving station. This is a map of a bunch of the receiving stations. A lot of the data was held at those receiving stations. They get it down, they put it on tape, and it sits there for years. So starting in the Landsat 5 era, 1984, data come down and sit on tapes from 1984. Recently, the USGS has started pulling that data back into the US archive, and it's been quite a feat trying to decode a 20-year-old or a 30-year-old tape. There's some other interesting challenges with data in remote receiving stations. There's a story about getting the data out of Ecuador. There was an agreement reached between the USGS and the Ecuadorian government. Yes, you can have the data back. They were about to load tapes onto a boat, and the army stopped in and said, nope, you're not taking those tapes out of the country. So those tapes couldn't leave, which is an interesting curation challenge when you can't get your data back to your curation station. Additionally, some of these tapes are 35 years old and they haven't been stored in the most pristine of conditions. So they often have, say, mold on them. And to read data off of a tape that's very old, you usually have to heat it up in an oven. You basically bake it, get it all nice and malleable, and then you read the data off of it. So imagine putting a moldy tape into an oven. They do this job in hazmat suits so that no one dies. So it took 3 years for us to get data, all the data out of the USGS that they had at the time. This is a graph of data downloads out of their system. The reason it took so long is that they keep all their data on tape and they process it on demand. So you say, I'd like this scene, goes into a system, gets processed. An hour later, you get an email and they say, here's your scene. Now that's not so bad if you want to work on 1 image. If you want to work on 10 images, okay, you wait a day, you get your data. If you want to work on 100 images, that's kind of a problem. If you want to work on 2 million images, no one had ever done it. It had never been done. So it took them 3 years to process all that data. We got it out of them. And when you've got all that data, one thing you can do is you can look for the best pixel to make an image out of. So in this image, which I think is South America, you can see there's a lot of clouds in this image. This was actually the Google base map inside of Google Earth and Google Moon, excuse me, one more time, Google Earth and Google Maps in 2012. And you can see green bits in there and brown bits in there, but the clouds basically obscure everything. But if you've got all the images, this particular spot was imaged several dozen times, maybe as many as 100 times. Now I've got 100 images to choose from for each pixel. Maybe none of them are completely cloud-free, but I can take 1 pixel out of every image that doesn't have a cloud in it and composite together something that looks like this. And so now you can see individual farms, individual roads, the coastline very carefully. There's a bit of fuzziness on the edges there, some striping. That's from one of the Landsat sensors that had a broken mirror. So it isn't perfect, but it's way better than the thing that we had a minute ago. Here's another example. I think this is one of the islands in Great Britain. That's before. This is after. Again, it's a place that's always cloudy. It just so happens that you can see through some of the gaps in the clouds over enough time to be able to get a whole image. Here's South America before. Here's South America after. So, got all this data, you can process it, you can do cool stuff with it. So, we downloaded 29 years of satellite data, 2 million scenes at the time, almost a petabyte of data, processed the heck out of it for 2,000 CPU hours. We're Google. What do you suppose we did with it? We made a video. That's what Google does, yeah? So you can see in this image, there's some squiggly bits. They're white, they're blinky. That's seasonality that you can see up at the North Pole. This isn't a particularly interesting video until I tell you that it's a 24 terapixel video. So you can zoom in to any spot on the planet and look at what's gone on for the past 30 years at that point at full resolution. So what we did is we took all the images from every year, found the best pixel at every location, and made 1 complete image for the year. So we have these annual composites. We then took all the annual composites and put them together as a series of frames in a video, and now we've got a thing where we can zoom in anywhere and see what's going on. This is Las Vegas. Las Vegas is on the right. You can see it doubling in size. Lake Mead is on the left. You can see it halving in size. Draw your own conclusions. People tell me this is not actually causal, it's just there's a big drought, but clearly this is a bit of a scary situation going on here. Yeah? This is Saudi Arabia. In the late 90s, Saudi Arabia decided they didn't like importing all their food, so they put a bunch of farms in the Arabian desert, pulling water up out of the aquifer. Not much water there now. At the end of this video in 2012, you can see a lot of those farms going fallow because they're running out of water. But it's still pretty cool, right? And I love this image because we have a word for this. Humans have a word for what's going on here. This is called terraforming. If we go to another planet, this is what we're going to do to it. As we built this video, we knew that we'd see things like Las Vegas doubling in size and these farms because humans affect the world, right? We knew that was going to happen. We knew we'd see those things. These are things we never thought we'd expect to see. These are rivers in Bolivia. all the little channels in the landscape that you can see in any one of these images are oxbows, right? Everybody knows, or most people know, that rivers meander and leave channels when they go along. We never expected to see them at this scale. So I love staring at this. We still spend hours just staring at these images. Kind of see the river slamming into that little town. And they knew it was coming, right? The town's curved right there. They're building on the backside. They're not building on the side where the river was. I'm guessing because it's swampy, maybe not a good place to build, but it's still pretty impressive. All right, I'll let you stare at this one for a second. You see my mouse up there? Yeah, you see this? This is a river being born. No one's ever seen this before. So we have some river morphologists that are, wild about finding things in these images and basically rewriting textbooks, right? If you've never seen this happen before, it's a process that's undescribed. They're off busy describing processes. So we built this thing, we called it TimeLapse. We launched it with Time magazine in, I think it was early 2013. We gave you you could go to Time magazine, you could view it, you could come to our site, you could view it, but you could also put it in your own web page. So we had this embed feature, stick it in your own web page. And millions of people looked at this, not only on our website, but lots of other websites. So we'd wake up some Monday morning and see 30,000 hits from some little town in the Ukraine. It's like, what's going on? So we'd hunt down, trace back, see what's going on. And it turns out that the local Ukrainian newspaper published an article about when the dam went in 1987, this happened to the town. And look, you can see it happen. And they published a link to TimeLapse on their website. And every single person in the town goes and looks at the data. And this is exactly what we were hoping for. Democratization of this data. The ability for people that have no idea what Landsat is, no idea what remote sensing is, that would never have been able to process this data, let alone get it, now have immediate access to it. They're able to just grab it, use it, start using it to make decisions, and have it affect their lives. But even though this was cool, the most important part about this project is that after 30 years, my mom finally knows what I do. So, hi Mom. She's always said, I don't understand it. When she saw this, now she understands it. All right, so what? So we made a video, big deal. Story number 2. Those guys are the Suruí Indian tribe in Brazil. They live inside that little polygon, which is a protected piece of the Amazon rainforest. And they actually patrol the border with bows and arrows to keep loggers out, okay? All that stuff, all the light green around the dark green is subsistence farming that is cutting into the Brazilian rainforest. These guys got the Brazilian government to say, that's your land, you do what you want to with it. And they said, we live on the forest. We don't want farms. And so it's up to them to keep people from logging their forest. So they talked to my boss and said, look, we need some help. This is the scale of what's going on in the Brazilian rainforest. It's disappearing at a rapid rate. The deforestation is visible from space. We just need the ability to detect it. Help us out. And we thought about it and said, okay, that's something we can do. And so we built them a tool, and it looks like this. And in the second half of the presentation, I'll actually live demo this tool, I hope. But it goes about like this. This is a composite from a bunch of Landsat data. You can draw some polygons on it saying this is forest, this is non-forest, and a few seconds later, you've now got a map. You can make 2 of those maps, you can difference them, and you can say, there were trees there last week, there are not trees there this week, maybe we should see what's going on. We call this a good enough map. It's not necessarily a map you'd publish in a scientific presentation. In fact, you shouldn't. But if you're the guy on the ground who has one 12-year-old computer, a cell phone's worth of bandwidth, and probably not even a high school education, and in many cases he doesn't even speak English, this tool is something he can use with 5 minutes of training to make a map good enough to let him do his job. That's the leader of the tribe. He's really good friends with my boss. And they have really good Wi-Fi in their forest. All right, so now we're on to what we actually did and why. So we're a project that was incubated in google.org. That's the arm of Google that is doing philanthropic work. So more or less, they get 1% of Google's revenue and resources to go make the world a better place. And one of the things they did was incubate our project to help stop global deforestation. But really, it's got a bigger purpose. That was just sort of our first application. The real goal is to operationalize science. So in the US, at least, what often happens is that a scientist will get a grant for some research project where he's attempting to build a deforestation detector or an urbanization detector or fire detector, whatever it is he's looking for. He will spend his $3 million getting all this data, processing it, producing his results, writes his paper, done. I made a deforestation detector, now I'm off to something else. And that science will often just sit there. Someone that wants to reuse that will have to re-implement it themselves, probably. It's getting better now. There's open source projects where a lot of the code lives on. But still, it's not his job to get that tool into the hands of people that need it. His job is to do research. And if someone wants to use that tool, it's their problem. This doesn't have to, we don't like that, and this doesn't have to be the way it is. If the project is built on top of a platform that will just let you run it, then there's no cost to the scientist to be able to pass that algorithm on to the next guy who can then use it and build on top of it and either build more complex algorithms or use it operationally to stop deforestation. When you start a project at Google, you have to list all your goals and your non-goals, and so these are our goals. Basically make science better, but what it really boils down to is we're trying to make the world's most advanced geospatial analysis platform. And what that means to us is that if you're able to use an existing tool to do what you need to do, we're not the tool you want, right? Our goal in life is to do the things that are not possible anywhere else. If you want to process 1 Landsat scene, 10 Landsat scenes, 100 Landsat scenes, plenty of tools around to do it. You want to process 1 million Landsat scenes, there aren't a lot of places you can do it. That's where we kick in. So, dig a little bit further into this. What do we really mean by building the world's most advanced platform? And why? We want to build it so we don't all die. And that's a little hyperbolic, but what that really means is that we're trying to solve the world's biggest challenges. And this is what we think about on a daily basis. These are the challenges that we're attacking. Deforestation, drought, disease, famine. And again, people die from these. These are things where good mapping can actually have a pretty significant impact and reduce loss or increase gain in those areas. So some examples of some of the projects we're doing in these areas. This is a map made with Professor Matt Hansen at University of Maryland, which is the first global forest extent and change map made at 30 meters. So it's a global map, shows you everywhere that forest has come and gone over the past 10 years. Took about 1 million CPU hours, used the entire Landsat stack. Paper came out in Science in late 2012. Again, first of its kind, and really the first of a series of projects that are exactly the sort of thing we're trying to tackle. This is a project with the Desert Research Institute where they're doing drought monitoring, not just monitoring, but flash drought monitoring. What are the conditions over the past 6 to 8 weeks so that you can direct resources, do water conservation where necessary. This is a project we're doing with the Joint Research Center in Italy, where we're mapping global surface water. So just like the forest and deforestation map, which is 30 meters everywhere, this is water at 30 meters everywhere. And this one actually has a full time series component, so you can go see exactly what has happened to that water every month for the past 30 years. One of the applications that they're directly using it for is rangeland management in Africa, where people drive their cattle from watering hole to watering hole and use the fodder along the way. One of the things they want to do with this is have a probability for whether or not that water hole you're going to go to in 2 weeks is going to have water in it or not. So based on past seasonal variants, we can say, don't go there, you won't make it. You should go over here instead. This is a global crop map being made with the USGS. It's actually crop, no crop, crop type, intensity, and irrigation source, I think is the fourth layer. This is a project we're doing with University of San Francisco, where they are trying to do early alerting for malaria. This is a map in Swaziland, I believe. The idea is to predict where malaria is likely to break out and then direct resources to those locations where aid has otherwise not been delivered. So if you know that there's two villages and they're both in the risky area and one of them has had mosquito nets issued and one hasn't, perhaps new mosquito nets should go to the village where they haven't gotten to yet. So couple this with on-the-ground aid to try to help eradicate malaria. This is a project called this is a project by David Lebel at Stanford. He's mapping a property called VS30, which is the shear velocity at 30 meters when an earthquake happens. Here's a simulated fault in California. When that fault triggers, this is the expected intensity of ground movement. So basically, it's a danger map. If this fault goes, don't be in the red spots. And this is a global development map made from nighttime lights data. And in the second half of this talk, I'll show an interactive demo again with this data, and we can zoom in and look at some of the interesting bits in it. So I've shown you why and a little bit of what, but I haven't really told you what this thing is that we've built. So it's essentially a big data platform for remote sensing analysis. There's a word missing there. What that means basically is Google's got a lot of computers. We get to use them for remote sensing data. We've got a really nice user interface on top of this and a gigantic data catalog underneath it ready to use. So if you use us, this is probably the interface that you would use us with. It's a JavaScript map on the bottom. There's a box on the upper left, which is sort of inputs, documentation, assets, those sorts of things. There's an output box on the upper right where things that you're printing or charts, those sorts of things go. And then this box in the center is, we call it the insert your science here box, right? If you're familiar with MATLAB or IDL or one of those interactive programming environments, those will be very similar. You start typing in the box. When you've got a script that you're ready to run, you click the run button and your results come up hopefully in a few seconds. And that's what we shoot for, is a couple of lines and 7 seconds to get the result you're looking for. Perhaps not your entire analysis, but if you take your analysis and you break it down and say, okay, I want to mask out clouds. Okay, that should be something that we should be able to do in 2 or 3 lines and 7 seconds. If you then say, I want to compute variability, okay, again, that should be a couple lines or maybe 1 line and a few seconds. It is possible to put enough of these pieces together that it takes much, much longer than 7 seconds, but the point is you stick all these primitives together and build the algorithm that you want based on top of us. Nowhere along the way did you have to worry about file formats, resolution, projections, downloading, how many CPUs, where they're going, are they up, are they down. All those IT problems have been removed, and you literally show up, insert your algorithm, and click run. This happens to be a map of phonology. So this is another demo, but I'll explain it real quick. What we've done is we've taken the data from the entire Landsat? Yeah, the entire Landsat 8 archive, and converted it to a vegetation index, which indicates how much photosynthesis should be going on. And then we fit a harmonic to that. And the phase of that harmonic is plotted in color. So the things that have the same color are probably the same crop, because crops have peaks at different times. So this is a peak of the sinusoid map, and things that are different colors are almost certainly different crops, although there's not a lot of different colors here. All right, so I mentioned that we have a very large public data catalog. Currently we have, let's see if back up one. Currently we have about 6 petabytes of data. That includes now 6 million Landsat scenes, about 20 MODIS collections, a bunch of terrain data, a bunch of climate data, land cover, all of Sentinel-1. We're loading up Sentinel-2. If you're a remote sensing guy, this is very exciting. If you aren't a remote sensing guy, this is a bunch of data from a bunch of satellites, but the data that you use to then go detect things. We update these images on a daily basis at a rate of about 6,000 a day from all the various sources that we pull data in. Yeah, we'll go forward. So, what can it do? What do you do with this thing? Well, we've got this big giant data catalog. One of the easiest things you can do is just get an image from it. So this is some Landsat scene. If you're a remote sensing guy, this is there's a similar tool in the open source community called a map server, which lets you get an image, but in any projection, any resolution, with whatever bands you want, and any visualization applied to it. Real simple process, but get an image out and let me look at it. You can apply an algorithm to an image. So the Insert Your Science Here box is a place where you build algorithms and they apply to images. We've got a library of about 800 functions that you can chain together to build your own analysis. And we also have a bunch of pre-built analyses that you can just run on top of it. Again, nothing real spectacular here. This is exactly what you do in MATLAB or something like that. When we have these really big piles of images, like all of the Landsat data, we put them into collections. And it may be or it may not be that you want to work with all of them at once, so you can filter your collections. You can say, just give me the scenes over Stockholm for March of 2005, or all of the growing season for the past 10 years. Lots of different ways to filter that data. Once you've got a collection that's filtered, you can now map an algorithm over that collection. And this is where the computer science stuff starts to kick in that you don't need to know, but my computer science guys have put together for you. So Google popularized a parallel processing technique called MapReduce. Mapping an algorithm over a collection means applying an algorithm to every element in the collection. So every image in the collection. If you are detecting water in an image and you've got 1 million images, you want to detect water in all 1 million images and get your result out the other end. So that's called mapping. If you aren't using Earth Engine and you're doing MapReduce, you're probably working with a computer science guy, or you spent a lot of time figuring out how to run MapReduce yourself under something like Hadoop. The other half of MapReduce is reducing, where you take the collection and you compute some summary statistic. You might squish it flat to make a mosaic, but it's essentially mapping is a many-to-many operation, essentially applying something to everything, and then reducing is a many-to-one or a many-to-fewer operation where you reduce the data down to a smaller amount. And then you can compute an aggregate over these results. If you want to do some global zonal statistic, how many hectares of forest were lost, that sort of thing, those sorts of global analyses are often endpoints for what we do. All right, so there's some things that we're good at and some things that we're bad at. We are good at things that are naturally parallelizable. When we do processing, we process things on a tile-by-tile basis. We load an image, we cut it up into a bunch of tiles, and basically process on each of those tiles, distributing each one to a separate machine. And since we have roughly an infinite number of machines, we can handle roughly an infinite number of tiles at the same time. So through this process, we're able to have very, very fast results. This means things like band math, spectral unmixing, classification. Those are things that we're very good at. Things that we are very bad at look like finite element analysis, things that are non-local. So a real good example of this is watershed. It rains on the top of a mountain and the water ends up in the ocean. Compute the watershed. That's a very non-local operation. It's very difficult to do with tiles. That's an operation that's almost impossible in us. So if you have an analysis that fits into one of the grooves we've cut, it's very easy and very fast to do. If you happen to be in one of the grooves that we haven't cut, which wouldn't be a groove then, sometimes it can be very difficult to use us. All right, so that's my talk. The second half of the talk will be demos about using us directly, but I'm supposed to give you guys a break in the middle. you bet, I was going to take some questions. If you want to come play with us, you can sign up at earthengine.google.com/signup. And thank you very much.
So, are there some questions? Okay. Are there some questions right now?
Ooh, no questions. I did a bad job.
Oh, yes, there is.
So the question is, how do you map malaria with Landsat? And the answer is, you kind of don't. What you map is the environmental variables that are conducive to the breeding of the mosquitoes that deliver malaria. And that tends to happen with precipitation, vegetation, temperature. There's probably one more in there. So you can get the local temperature from Landsat. It has a thermal band. You can do a vegetation index from 2 of the bands in Landsat, but the precipitation you have to get from somewhere else. And so that's one thing that we're actually very good at, is bringing together all these disparate data sets. So it's quite easy to grab a composite out of the Landsat, make a composite out of the Landsat collection and grab the rainfall data that goes with that date and get these combined covariates that you then put into a model and predict malaria at a future point. It's very hard to predict forward in terms of vegetation index and temperature, but you can use last year's numbers or a cycle of numbers to say, we expect it to be X temperature next month, and there are forward forecasts for precipitation that let you predict what the precipitation will be in the future.
More questions? Yes.
The question is, do we have anything other than Landsat, basically? And the answer is, we already have all of the Sentinel-1 data and being processed right now, ready to be used, and we're working on the Sentinel-2 data right this minute. We have data from about 14 spacecraft, including those 2. So yes, we want to make the data available that's useful. An important thing to note is that all of the data we have, besides the original Landsat collections, we have because someone came to us and said, if I had X and Y, I could do Z. And X is usually a data set, or 6, and Y is usually an algorithm that we don't have. I build the algorithm, my data guy brings in the data, we enable him to go forward, and he produces a new data set. So if we don't have a data set that you want, but it's otherwise freely available, you just let us know and we go and get it. I didn't mention, I guess I perhaps implied it, but Earth Engine's free to use. In fact, you can't buy it. It is not for sale. It's, again, a philanthropic effort, and we are primarily oriented towards people that can drive an impact to the ground, but that means it's free for academic and research purposes. So you can show up at any time and say, hey, I need the data from this particular satellite, and I want to do that with it, and we'll do our best to accommodate you.
More questions? Yeah.
You catch non-local operations, non-local kind of functions, like vision analysis, or probably I can guess like distance analysis, or maybe finding a path from between 2 verified locations. But do you have any future plan or current status that you can share with us? How do you address these non-local operations?
The question is, we're not good at non-local operations now, but will we be better in the future? And that's a little bit of a misleading statement. We actually can do non-local operations, but the more non-local it is, the worse we are at it. So anything in which you can give us a finite horizon, even if it's a pretty big horizon, we can do just fine. So if you say, I want to know distance to nearest water body, and I don't care about things further than 3 kilometers away, or 30 kilometers, or 300 kilometers, then now we have a bounded problem, and we can appropriately allocate resources to solve that problem. If you say, I want to know nearest water body anywhere on the planet, that's a much harder problem, and we don't know how to solve that. A lot of the problems that we have are problems that haven't been solved, period. So there's a lot of algorithms in which there just doesn't exist a parallel or distributed version. No one's invented it yet. My guys are smart, but there's only a few of them, so we tend to not spend our time inventing those algorithms and instead implementing the ones that do exist.
More questions? If not, I would like to ask a question. In our conversations, you talk about that you also have data on individual buildings, building heights. I know currently globally available data at mid and low resolution. So would you be willing to release this building information eventually on Google Earth Engine? Because we have real estate economics students here, so they might be interested in analyzing more local level.
So let me turn that question around just a second. One of the things that we do with Earth Engine internally is map things. Perhaps you've all used Google Maps, I would hope. That's technology driven. The data in there comes from various sources, one of which is Earth Engine. So we have analyses that detect buildings, detect roads, those sorts of things, and we build a big database of this. That data is all from the commercial side of Google, so it's unclear whether or not we can make the building database available for free. But on the other hand, we don't sell it either, so it's not quite clear how we might get access to that data. But it's something that we constantly strive for to try to make good data sets available, even if we're the ones that generated them. So in short, not yet, but we're working on it.